Hello, my name is David Themens, and I'll be talking about a near real-time high-latitude ionospheric data assimilation system, which I guess what I'll be presenting is a newer version of the Assimilation Canadian Higher-Tech Ionospheric Model, or ASHAME, that's currently available at the University of New Brunswick. I'll be presenting the work on behalf of my PhD student, Ben Reid, who developed the majority of the system in collaboration with myself and Anthony McCaffrey, who did a lot of the front end data acquisition components. So to give you an outline, I'll start off with a description of the background model. This is particularly important for this type of data assimilation system because the background model also makes up a lot of the basis set that we use for the data assimilation, so our state space. I'll then talk about the data set and the data assimilation scheme itself. Before getting into some performance assessments during the September 8th, 2017 geomagnetic storm and also the March 2013 geomagnetic storm, or St. Patrick's Day storm. ASHAME is an empirical model of the high latitude electron density above 50 degrees north geomagnetic latitude. It's designed as an alternative to the use of the IRI at high latitudes and was built on probably one of the most extensive data sets ever really assembled for empirically modeling electron density, particularly at high latitudes. This is made up of several million ionostone observations, as well as a couple million inquiry and scatter radar, array occultation, and topside sounder observations that make up the top side of the model. This is just an illustration of the domain of the model. It's just a plot of FOF2 in megahertz, where from ASHAME, where the red solid line here is the lower boundary of the model, or the recommended lower boundary of the model, and the dashed red line is the lower limit at which the model will provide output. So we don't recommend using the model below this red solid line, but we do provide data or output down to that dashed line in order to create a region for merging with other ionospheric models, say like the IRI. The horizontal variability in the model is given by the spherical cap harmonics, which will form the horizontal component of the state space that we'll be using in the data assimilation scheme that I'll present later. The vertical structure in ASHAME is a peak fixed model, so we model NMF2 and HMF2, and we anchor a semi-Epstein layer model to that HMF2 and NMF2, and then simply model the vertical structure of the ionosphere by virtue of a model of scale height rather than electron density itself, where the scale height model is, or a representation of the scale height space of the model is given on the bottom here for this electron density profile up here. So we have a number of functions that create the curvature in the bottom side, creating the F1 layer in the E region. And then we have a transition between the bottom side F region thickness and the top side F region thickness, where in the near peak regime, the top side scale height is given by this, but as you go to higher altitudes, this top side thickness actually becomes asymptotic. So the reason why I mention this is because the state space, or the state space, or the vertical component of the state space in the assimilation system I'll be talking about uses this parameterization. So we don't actually assimilate into voxels as one might conventionally do. Instead, we do a highly nonlinear data assimilation where we assimilate into a basis set or a state space of spherical harmonics for horizontal variability and the individual ASHAME components for vertical variability. In terms of data sets, we incorporate the global observations from GNSS. So the blue dots here are the GNSS that we assimilate in near real time. This is, by near real time here, I mean available on the hour or better. And on the right, we have a number, or the blue dots are giving the GNSS stations that are available but aren't available in real time. So these generally provide their data on daily timescales. so at the end of the day. I've also plotted out in red the locations of ionospheres that are incorporated into the system, where I'll talk about this in a little bit. But so this is our assimilated data, and then this we will use or during the test events I'll show later to validate the data assimilation system as our reference data set. This is just an illustration of the global the distribution of ionospheres above 30 degrees north magnetic latitude. The purple dots are digisones available from GIRO. The red dots are chain ionospheres, which are not available in real time because they have to be manually processed, so they're not assimilated into the system. Blue are the ionospheres operated by the Russian Arctic and Antarctic Research Institute, and the orange are ionospheres operated by Roshydromet, which to some extent I believe are most of these are at least available through GIRO as well now. In addition to ionosphere and GNSS data, we also incorporate JSON data, which is generally available with a latency of less than, better than or 2.5 hours, usually about an hour and a half, where JSON provides integrated electron density from the satellite orbit down to the ground over the oceans, which is a considerable benefit to a data assimilation system, given that our predominant observation data set, GNSS data on the ground, is not available over the ocean. So this acts as a nice regularization data set for the ocean areas. What I'm plotting here is just what the data set looks like for a 2-hour span from JSON 1 or 2 and 3. So the system itself, realize this is a large wall of text, but as I mentioned before, eShame, or this data assimilation system, uses the eShame basis set as its state space. So we parameterize the vertical structure with that scale height function that I talked about before, HMF2 and NMF2, and then we characterize the horizontal variability of spherical cap harmonics. This substantially reduced state space in comparison to, say, using voxels allows us to use particle filters, which are kind of the ideal assimilation framework for assimilating in highly nonlinear systems. So the disadvantage to particle filters generally being that they're incredibly computationally expensive, especially in comparison to something like, say, a Kalman filter or an ensemble Kalman filter. The specific framework that we use is a sequential maximum likelihood particle filter scheme. And you can almost think of this data assimilation system, because we're using the spherical harmonics as our horizontal basis set and so on, you can think of it almost as like an IR-TAM data assimilation system, but instead of just assimilating FOF2 for FOF2 maps and HMF2 for HMF2 maps, we can assimilate any observation we want that has a constraint on the ionosphere, hopefully no matter how nonlinear it is, to constrain the entire 3D structure. So we can get a constraint on FOF2 in regions where we don't have ionospheres by virtue of having GNSS receivers in that region, or by virtue of having, say, SuperDARN coverage over those regions. In addition to this, the system, by construction, we've decided to solve the receiver biases for GNSS receivers within the basis set, which actually makes up the dominant portion of the basis set. Simply because there are so many GNSS receivers assimilated, which allows us to avoid any assumption errors or systemic errors that tend to kind of plague conventional GNSS receiver bias estimation techniques. And as I mentioned, for near real time, we assimilate ground, spaceborne GNSS or GPS receivers, altimeters, ionospheres, and ray occultation. However, there isn't any ray occultation currently available at high latitudes, given the canceling of Cosmic 2's polar orbits. But for a retrospective version of this, which is, or I guess, also under development, which we call RShame, It can assimilate virtually anything. So this adds in situ data, it adds in concurrent scatter radar data, non-real-time POD tech, and rail occultation tech as well. And then in the future, we anticipate also assimilating more nonlinear observations from, say, Goofy or Suzy, as well as observations from SuperDARN and so on. In terms of workflow, at any given or on an hour, say at 5 here, we're constantly aggregating data. Okay, and so on the hour, we go back 4 hours and assemble a data set of all data available from that 4 hours ago to the current time, aggregate that into a single data set, and then run our data assimilation system forward. Originally, this was only run forward to an hour from the current time, as our GNSS data, the vast majority of that comes in on the hour. So we tend to start running out of data after an hour from the current time. However, we've now extended this to also go to the current time, as well as extrapolate out the 1 hour into the future, just allowing the assimilation to kind of relax back to the background after data is no longer available. So the colors here just illustrate the data availability for these assimilations. So you can see in general, GNSS data tends to stop from at the hour prior to our run, whereas Ionosonde, JSON, or Ionosonde and ISR data tends to run directly to the time that we begin our assimilation. I should mention that ISR data was not assimilated into this into any of the runs that I'll talk about here today, but there is real-time ISR data available from the SRI operated ISRs at Poker Flat and Resolute. So prior to beginning a validation of the assimilation system with respect to ground-based GNSS from all those reference GNSS receivers that I talked about prior, it's important to kind of get an idea of what the kind of error budget is with eShame. So what errors typically exist in eShame that we can kind of where we expect to see improvement from the assimilation system, because we know that eShame has some substantial errors in those regions. So on the right here, we have on the top the RMS errors arranged by geomagnetic latitude on the y-axis and time on the x-axis from eShame. And then on the bottom, we have the same for the RI, just for context. Note that there are different y scales here, or contour level scales here. And you can see in general, below the auroral oval, eShame tends to have more substantial errors. And within the polar cap, eShame's errors are on the order of the measurement precision. Except for maybe at high solar activity where errors increase a little bit. So we can expect that a data assimilation system should be able to improve our representation at subaraural latitudes, and should, at least at high solar activity, also provide some benefit at within the polar cap and auroral zone. So September 2017, we have a reasonably good geomagnetic storm on September 8th. This is just a plot here in pink of the DST during that storm, and the purple is actually the number of ionosones that were available at any given time. And you'll note that once the storm begins, there's a bit of a blackout in terms of ionosone data availability. We start effectively, very typically, as one would expect with particularly high latitude ionosones, they tend to become less reliable as conditions become more dynamic or are completely blacked out by storm conditions. The bottom plots here are the RMS differences between the assimilated data and the assimilation system. So this is for FOF2, vertical to electron content and slant, or vertical to electron content from JSON, sorry, and slant to electron content. So generally, after a little bit of burn-in, we're able to improve upon the background model's representation of the measurements, so background given by black and the assimilation system given by blue. Obviously, this is expected. This is with respect to the data we're fitting to. The main point of looking at something like this is to just check to make sure that we're not doing too aggressive of a job in terms of overfitting our data set. And as you can see with the slant collection content, we're generally approaching our measurement error. So we haven't done too bad, or we're not, I guess, burning into our data. So if we look at the unassimilated data or the reference data, first we can look at a time series of slanted electron content errors. Again, the RMS here is, or these are RMS S-Tech errors from eShame in black and from the assimilation system in blue or red, blue being better than the background, red being worse. And you can generally see that the assimilation system does a considerably better job at the significantly reduces the error in slanted electron content with respect to the background model. And these improvements are particularly located at suborbital latitudes where we generally have the largest errors in eShame. As one tends to higher latitudes, the improvement is a bit less impressive. But you'll note that if we go to, say, the period after the storm here, September 11th, 14th, the errors, it's not so much that the assimilation system is getting worse than the background, but background is actually getting considerably better. And so the reality is the background is actually in the error or in the measurement noise domain here. So we can't really produce much improvement. We can go to those geographic representations from before, and you can see again, most of our improvement is in continental United States at suborbital latitudes. Interestingly, Alaska, which if we look like during the day prior to the storm and the day of the storm, you can see considerable improvement in Alaska and even some improvement in Greenland, which had no data available to it from, or maybe 3 GNSS receivers available to it in near real time. So we're getting considerable, we're actually able to get improvement in areas where we have very sparse or limited data. Same for Alaska, there are only about 3 GNSS receivers, although there are some ionospheres there. As the storm progresses, particularly on the day after the storm, we see a little bit of muddled performance where things are better than the background at suborbital latitudes where the errors are larger, but slightly worse in the polar cap where we don't have much data. And because we're using these fairly coarse spherical harmonics as our basis set, high latitudes, which will have a lot of small scale structuring, aren't going to be resolved by this basis set. And so a lot of this error could simply be coming from the inability of our basis set to capture the structuring that's causing these errors. Next up would be 2013. This is just a quick plot of FLF2 and HMF2 from the resolute ionosphere, which was not assimilated and has no nearby ionospheres to provide information on the vertical structure of the ionosphere. And you can see the assimilation system in red, ionosphere in blue, and black is the background model. Prior to the storm, there's actually a considerable offset between the background model and observations, which is corrected by the assimilation system. As the storm progresses, we do see a lot of patches and other structures that make it very difficult for the assimilation system to improve upon. However, in the recovery, we do start to capture some of the larger scale structures, let's say with the storm, but generally very limited improvement, as one would expect, really, given that there are very few observations in the region around this ionosphere. Similarly, we can look at HMF2, and there are some minor adjustments to HMF2 prior to the storm, which again are a nice little benefit. And we do get a little bit of lifting of the ionosphere during the storm, as one would anticipate physically, that is really only coming from the GNSS data. So it's actually kind of impressive that despite having very little Ionospheric or any data in this region, we're able to actually get a little bit of an HMF2 bump during the geomagnetic storm. Going down to Juliusra, which also wasn't assimilated, but is in Central or is in Europe, where there are a number of additional ionospheres in the neighboring region and a very dense GNSS network. You can see obviously the assimilation system is doing a pretty good job at reproducing the variability at Juliusra, not only in advance of the storm, but also during the storm itself, where we capture this nice positive ionospheric storm effect. You can see ahead of the storm, these daytime conditions are really well matched, but you'll notice that at night, we do have a bit of a struggle getting the assimilation system to migrate away from the background model. And this likely comes from the fact that at night, the densities are quite low, which means that the densities are lower with respect to the, the measurement precision or the measurement error of GNSS data. And so we start to get into the weeds, or we start to get into the measurement noise here, and that makes it very challenging, even in a region with dense observations, to overcome just the noise characteristics or the phase leveling errors and all this other stuff that comes with GNSS data, even horizontal gradient errors that we can't resolve. For HMF2, you can see generally not much of a change, except for during the geomagnetic storm, where again you can see we do get this improvement where we get some lifting in the assimilation system during the geomagnetic storm, as one would expect from electrodynamic lifting. We can look at Poker Flat, where the top here are vertical profile or a time series of vertical profiles from the current scatter radar. Middle is from the assimilation system, and the bottom is from eShame. And generally, you see that eShame does a very good job just to begin with at capturing the storm variability at Poker Flat. However, it generally underestimates electron density in the F region. And the assimilation system does a pretty good job at inflating or increasing that electron density in the F region and making a better representation of the ionospheric storm, or the conditions prior to the storm, and thus the response of the ionosphere to the storm. We can also see some improvement in this recovery over here as well. Looking at the differences between the errors from the background model to the assimilation system. Blue is improvement with respect to the background from the assimilation system. So you can see generally in the F region, we do a pretty good job at improving upon the background. During the storm itself, where small scale structuring becomes a problem, and in particular in this case, where auroral precipitation becomes a problem, we see some degradation of performance. So with our data set being predominantly GNSS data, and our basis set not having a means of, accommodating for auroral precipitation, E region is not a strong component of this basis set, and there's no particle precipitation in eShame at this point. The total electron content from the aurora has to be attributed somewhere else along the ray path in the assimilation system, typically in the F region or in the bottom side thickness. And so this can cause, E region, or things that we don't account for in the E region can propagate into errors in the F region on the assimilation system. And this just highlights the need to incorporate particle precipitation into the assimilation system, as well as into the background model. So all this to say, we've produced a high latitude and real-time data assimilation system that solves for GPS receiver biases internally, and hopefully we'll produce these biases as an additional product to users. We use a technique that's very well suited to highly nonlinear systems, which will allow us to, in the future, scale this to incorporate other data sets that are also, or provide nonlinear constraints to the electron density of the ionosphere. The system represents an improvement over existing empirical, or the empirical background model, eShame, and a retrospective version of this model has been developed that will also incorporate substantially more data. Finally, particle precipitation is currently in the process of being added. That's it for me. Thank you for your time. If you want any further information about eShame or ASHAME, you can find all the source code freely available at our links up here. Thanks.